Okay, let's do this. So first of all, I didn't look up when is the next test is Friday in this class? Oh, that's right. That's right. So exam, it's a big day for Fred. Yeah, that's true. So exam 4 is Friday. Yeah. And the topics are everything up through macroscopic deformations, and statically indeterminate systems. And then, yeah, there's a quiz on Monday. Does anyone have any homework questions? Okay. All right, well, today is a redo. So the next topic, yeah. I did not forget. Yeah, so the next topic is column buckling. And this only applies, this analysis only applies to long, slender beams in compression. So, you know, short, stubby beams don't fail in this way. We're going to assume elastic, so this is based on the theory of elastic beams, and that means that at any point, the bending moment is equal to E times I times the deflection double prime. Well, actually, hold on. It's equal to E times I times the curvature of the beam. And assuming that the beam at no point gets too far from vertical, we can write this as the bending moment at any point is equal to E I times the second derivative of the deflection. Okay, so that's what this is going to be based on. And we're going to see that the compressive load that makes the beam unstable depends on the way that the beam is anchored at the top and the bottom, or anywhere along its length. So we're going to do the following conditions. We'll talk about beams that are pinned at both ends. We'll talk about beams, again, that are pinned at both ends, but this time they're also restricted somewhere else along their length. So I'll show this with a roller in the middle. So at that point where the roller is, there can't be any deflection. And then we'll do a case where it's fixed at the base and the angle is fixed at the other end. So I'll say for this one, the angle of the beam is fixed at both ends. And we'll do a beam that's fixed at one end and totally free at the other end. And we'll do one where it's fixed at one end and pinned at the other end. And based on these different conditions, so let's say that there's this compressive force P acting on all of these. The magnitude of the force P that makes this beam unstable, so it'll make it collapse in a buckling mode, is different for all of these. And so we're going to do an analysis of the differential equation to see which ones are, to see what that relationship is between buckling and the load P. And, we'll be able to see which one of these are more resistant to buckling and less. Okay, so I'm going to start with a beam pinned at both ends. So if you draw a free body diagram of the, well, let me just first draw sort of a picture of what's going to happen. So you have a pin down there. When it buckles, and this is exaggerated because we can't have big deviations from vertical for our assumptions to hold. But the angle isn't constrained here or here. And if you apply a big enough force P, then any force P, like any little motion or imperfection side to side, that lets it start to bow out even the tiniest little bit. It's going to be unstable at this point, and it'll keep bowing out until it snaps, in half in this case. Okay. So let's do a free body diagram so we can come up with the differential equation. And the basic differential equation is going to be similar for all these. There'll be one difference with all of them. Let's do the bottom half. And I'm going to do it in the deformed state. We have an upward force P from the pin and a downward P here. Our coordinate system is this, which means the positive z-axis is out towards us. And a positive deflection is this way. And there's one more load I haven't put in here yet. There's not any moment applied by the pin point, right? But since this is only half of it, or any part of it, I guess, but we're cutting it off somewhere inside the beam, there has to be a bending moment that's applied by the part we're ignoring to the part that we're including. So we have this force, this couple M. And what I did, so last time I drew it the other way, and it led to problems with the sign convention. I mean, if you think of any general calculation you do, when we did general calculations for internal loads, you always have to make sure that you're making the assumption, that the assumption you make goes according to your positive sign. And that's what I did wrong. I drew my picture with V going this way, and then one of two things would have to happen. Either you'd have to deal with the fact that I drew this negative and I didn't do that, or you would have, and you could do that by drawing out rho, force, M, do all that. It would have worked out if I would have done that. Or I could have made my positive V go this way, but then my relationship between V and M would have to be backwards. So one way or another, I had one thing negative and one thing positive, and it screwed everything up. But so now the only thing that I've changed is I've drawn my picture to reflect the fact that positive V is going to the left. And this does not make any sense. Okay. This is what I mean. This is X. Now that makes sense. Okay, so now it's clear that V needs to be, positive V is in the positive Y direction, makes sense, and all the signs will work out. Okay, so moment equation based on this free body diagram. We have the couple M, it's the bending moment. And then whichever one of these two you choose as the about point, it doesn't really matter, but let's say this is the about point. Then the moment here is a moment arm of V times the force of P, and that would make it rotate counterclockwise, so it's positive. So you have P times V, and for this to be in equilibrium, these equal 0. And now we'll make the elastic beam assumption that M is equal to EI V double prime. So EI V double prime plus PV is equal to 0. And so I'm going to rewrite this as V double prime plus P over EI times V is equal to 0. Okay, that's going to be the governing differential equation, ordinary differential equation for the beam pinned to the ground. So the examples that we're doing where the beam is pinned to the ground, well, there's only two of them. All of these are connected to the ground with a fixed joint. And so we're talking about these two cases. We'll have a different governing equation for those three. And so now we need to come up with a general solution for this differential equation. And this ordinary differential equation with a double prime plus something times the dependent variable itself is equal to 0. That's the exact same form that we're starting to talk about in dynamics. So this is just like mechanical vibrations in dynamics. Except that in this case, the independent variable is x. So it's the position along the beam's length. That's x, not time. But the form is the same, and so the solution, the general solution form needs to be the same. Anyone remember what the general solution form is? Yep. That's right. And then do you remember what the argument of cosine and sine are? It's so p over ei, and that's in the square root, times x in this case, plus b times sine of the quantity, square root of p over ei, x. Okay. And so now we have to use the end conditions, or things that we know about the shape, to figure out, like, what we really want is what we really want is the value of p where the system becomes unstable. And so here's where it's different from dynamics. We have the same general solution, but what we're trying to find is a different thing. So from here on, things are going to look different from dynamics. Okay, so what do we know? Now we're on to the boundary conditions. Well, we know that at x equals 0 and x equals L, deflection is equal to 0. Okay, so that comes from, we're dealing with the pin-pin case. The length of the whole thing is L. And so if this is the origin, we're saying that if you plug x equals 0 into that general function, you need to get a deflection equal to 0 because it can't move. There's a pin there holding it in place. And if you plug in x equals L, same thing. The deflection has to be equal to 0. It can do anything else in between, but we know it has to do that. So let's first do the one that says at x equals 0, v is equal to 0. Well, the deflection, so v at x equals 0 is equal to a times the cosine of all this times 0 plus b times the sine of all this times 0. And that has to equal 0. And cosine of 0 is 1, so this says a plus 0 is equal to 0. So we know that a has to be equal to 0. So I'll update this function for the deflection. Now we know that for this pin-pin case, the deflection as a function of x is just equal to b times the sine of the quantity square root of p over ei times x. Now we'll use our second boundary condition, and that says when x is equal to L, the deflection has to be equal to 0. We know that this is the form now, so I'm just going to use my updated form of the deflection function. And we have that the deflection at L is equal to b times sine of the quantity square root of p over ei times L. And that has to be equal to 0. Well, one solution to this is b equals 0. But we don't want that one. That's a trivial solution. That's the one that just says if the beam is straight up and the force is applied, it's an equilibrium. If the beam doesn't have any deflection anywhere, it's an equilibrium. We know that's true, but that's not what happens in buckling. So instead, we're going to require that we want the case where the sine of square root of p over ei times L is equal to 0. And that happens when the square root of p over ei times L is equal to n times pi for n equal 1, 2, 3, and so on. And now we just want to solve for this load P that makes this a solution in terms of all the other stuff. So square everything, you get P over EI times L squared is equal to N squared pi squared. and solve for P, and that's what we're going to call P critical. This is the P value where the trivial solution becomes an unstable solution. And P critical says EI times N squared pi squared over L squared. For N equals 1. Okay, so this is the solution. Well, yeah, so, okay, so what we have here is so this is the critical solution. This is, you can get rid of that 1 there, and you just have EI pi squared over L squared. That's the critical solution. Critical solution isn't the only solution. So there are infinitely many other solutions. Corresponding to all the different ends. But P critical is the lowest of those. And here's what these different solutions correspond to. So the first one looks like this. That's N equals 1. The second one looks like this. That's N equals 2. The third one looks like that. And then you can keep going on. But every time you increase the value of N, you're increasing that load P that's required to produce that solution. Okay, and so if there aren't any other restrictions on it, it's always going to buckle into this form, long before these are even solutions. So, but the other values of N are important. So it will always buckle into the N equals 1 mode at a load P that's below where these other ones are even solutions. Where the higher ends are solutions. I've noticed that if we have restrictions on points along the length of the beam somewhere, this isn't a solution anymore. Like if we said that this point here can't have any deflection because, like in the, so like in the next case, if you have a case like this, then that solution where it bows all the way out like that doesn't satisfy our restrictions. And so in that case, you have to find the lowest N value that satisfies the restrictions that you have. The one we have here, where the deflection is restricted right at the middle, that's just going to correspond to N equals 2. If you have a restriction a third of the way, then that's going to correspond to n equals 3, and so on. You have infinitely many chances to try to find a solution that meets your requirement. So if the deflection is restricted at another x value, between 0 and L, P critical is the solution for the lowest n value meeting that condition. Okay, so here's an example with those two. So let's say we have these two cases. Both of them are pinned at the ground, and pinned at the top. But the second one is restricted at its midpoint. So let's call this case 1 and this case 2. P critical is larger case 2 than case 1. By what factor? Yep. By. And so the solution is, so P is equal to overall solution EI times n squared pi squared over L squared. For case 1, P critical is EI times 1 squared times pi squared over L squared. For the second case, it's EI times 2 squared pi squared over L squared. And so I guess if I'll call this one P critical 1 and this P critical 2. So P critical 2 is 4 times P critical 1. By restricting points along the length of the beam, you can pretty quickly make a big difference, Yes.
If there's only one restriction, regardless of where it is, wouldn't it still equal n equals 2?
No.
If there's not another force keeping it from moving, it wouldn't do that of n equals 3. It would just follow the top bit, bottom bit more, right?
It would have to, let's see, so if it had, so you're saying like if it was restricted here and like restricted here and then up at the top, it would maybe do something like that. The solution says it wouldn't do that. And so, and the reason it wouldn't do that is because of the relationship between the bending moment and the curvature that says this thing has to have the same wavelength kind of over its whole length.
I mean, you could have material like this.
Mm-hmm. You could do it with, I mean, you can make shapes bend. You can make a thing bend in that shape, but we're not talking about whether you can shape it like that. We're talking about where there's actually a solution to that rotational Newton's second law that solves that. So, which is the idea of that is it's finding a point where we're going from. So, this idea of stable and unstable is that we're finding the p-value where if you carved out a little tiny bit out of the side, just took a little material away to take a little bit of that symmetry away, or just pressed your finger on the side a little bit to just gave it a little nudge. The tiniest little deflection here is enough for it to collapse all the way down because it goes from being stable, meaning if you nudge this out, that bending moment forces it back up into vertical position, to being unstable where you nudge it out a little bit, boom, like the bending moment isn't enough to counteract that force.
You look at it and it falls over.
Yeah. Yep. Okay. Well, and we did an example last time. Let's do one like we did last time where so let's say we have a beam that's pinned at both ends. And let's say it has a round cross-section, circular cross-section. With a radius of 1 centimeter. And let's say it's made out of steel. So Young's modulus is 200 times 10 to the 9 pascals. Bless you. And let's say that the length is 5 meters. What's P critical? And how does that compare? So how does that compare to the compressive load P that would just make it fail purely in compression? Okay, so we don't have any restrictions in the middle of the beam. So our critical compressive load for column buckling is E times I times N squared pi squared over L squared. I is equal to pi over 2 times 0.01 to the fourth. So that's 1.57 times 10 to the minus 8. So P critical is 200 times 10 to the 9 times 1.57 times 10 to the minus 8 times pi squared is 9 point something. What's pi squared? Pi squared. Divided by 5 squared. And can someone just tell me what that is? $1240.25 newtons. Okay, so now let's take this force and figure out in pure compression what the, okay, so now we're gonna do just pure compression. We'll measure the just compressive stress from that load. The cross-sectional area is pi times 0.01 squared, so 3.14 times 10 to the minus 4. And so sigma xx, that compressive stress, would be equal to, this is a compression, so that would be negative 1240.25 divided by this area, 3.14 times 10 to the minus 4. This is just equal to T over A, you know, the formula for that normal stress. And what do you get for this? Times 10 to the 6 pascals. And that's a small stress. You know, steel has no trouble dealing with stresses a lot bigger than that. But because this is a really long beam with a really small cross section, that load is enough to make it unstable and would cause it to buckle into that first mode. Any questions about that? I think if I remember, we're using the area moment of inertia, and I'm hoping that's what this is. So the area moment of inertia, that should be over 4. Is that? I don't know. I was thinking it was 2. It's 2. A polar moment of inertia is over 4. Okay. Any other questions? Okay, that's all.